You know, here's a function. It looks like it's broken into 3 pieces. Do you agree? I mean, just again, this helps me, even though this is totally inaccurate, this just helps me think that, you know, something is happening to the left of -3, and then between -3 and 1, between -3 and 1, there's something happening. And then greater than 1, there's something happening. Are you following me? I mean, that's when I see this, I'm just sort of giving you a quick outline of what's going on. When you read a piecewise function that's split into 3 pieces, I'm trying to quickly visualize it for you. And so what this problem turns into then is I'm investigating the places where they connect or don't connect. I'm trying to figure out if it does connect at those places, right? That's really what it comes down to, using this definition. Now, hang on a second. So, again, I drew an inaccurate picture. These aren't the pictures of these functions. But to the left of -3, do you have anything to worry about? Any undefined, No, you're a parabola, right? You should understand that a parabola is continuous always. So to the left of -3, I got no holes, no asymptotes, nothing to worry about. What about between -3 and 1? Anything to worry about? No, we're a nice line, I guess, right? If you think about it there, it's just some type of line, but nothing to worry about. What about to the right of 1? It's a cosine function. Cosine functions are beautiful waves. They have no problems. They have no discontinuities. So my problem is not left of 3, right of 1, or in between. Where are my problems? At -3 and at 1. I mean, so that's what you learn. But you better look sometimes. You better look out for some of those other places. But I really need to investigate -3 and 1. So let's do it one at a time, and let's use our definition. That's how I do it. That's how I think you should do it. At x equals -3, let's run through our definition. First off, number 1, can we find a function value? At -3, is it defined? Let's see. I should pay attention to the equal to here and plug in a -3 here, and I get -75, huh? Okay, well that's the actual y value for this function at -3. All right, well step 2 says I better investigate the limit as x approaches -3. But in a piecewise function like this, that really means I better investigate the left and the right. I need to investigate the limit as x approaches -3 from the left, and I need to investigate the limit as x approaches -3 from the right. It's a lot of writing to make this clear and set this up like this. But it's a lot of writing, but it's clear, I hope. Here I go. As I approach -3 from the left, let me think. From the left. That means I'm less than -3. If I'm less than -3, it's all about reading, paying attention to these directions. These are your directions. So when you're less than -3, you're up here and you plug it in, and what do you get? 46. When you're less, okay, I'm doing it from the left, sorry. From the left, you're less than -3. I'm using this, and I plug it in. I'm doing a limit. I plug it in, and what do I get? 46?
Yeah.
46. When I'm from the right, I'm greater than -3 on the right side of -3. I'm on the right side, I'm greater than -3. Perhaps I should plug a -3 in here. What do I get here? -75? That's me coming to -3 from the right. It's -75.
No. No, 65.
Oh,
Positive.
hang on. -3 times 20, -60 minus 15.
Oh, okay.
Negative 75? And since the left and the right ain't the same, it does not exist. And so, good. So he does not exist, and I don't have to go any further. I can go up here now and say at x equals negative 3, it is a discontinuity. I just discovered he's a discontinuity at x equals negative 3. And which type is he? Is he removable or non-removable? Good. I mean, I don't have a good visual necessarily of this, but I got this idea. When it fails the limit problem, it's a non-removable. When the limit does not exist, it's non-removable. So I'm going with that. Awesome. Hey, we're not done. Now we better investigate the other point. We better investigate that 1. See what's going on at 1. Sure.
So, why did you investigate negative 3 in the second formula or the equation, the problem, instead of the first one?
I'm investigating the point negative 3 on my number line.
Right.
I gotta look where I gotta look at on the left and right side of negative 3. I gotta be able to read this. X is less than negative 3. That's the when you're on the left of negative 3, you're using this to investigate the left side of negative 3. When you're on the right side of negative 3, that's what this says. X is greater than negative 3. You're on the right side of negative 3. You use this to investigate the right side of negative 3. I investigated the left and right side of negative 3 when I did this limit. I did the limit from the left and the limit from the right, and I got these two different answers. That was the key. The key was, yep.
Right. The first one, the one with the negative 3, that was lesson, right?
Yeah.
But it seems like you plugged it into the 20.
I think he's talking about the function.
Yeah, the function.
Why you chose the second one.
Yeah. So
Okay, for step 1, what was I doing? For step 1, I really wasn't checking out the left or the right. For step 1, I was trying to figure out what happens at negative 3. That's what that says. And so I was looking for where the little equal to sign was. Where's the little, see, it ain't equal to negative 3 there. Oh, there it is.
Oh, okay.
So when it's allowed to equal to negative 3, that's me finding f of negative 3, because x equals negative 3, and I plug it into the function, I pay attention to that, and I plug it in here.
Gotcha.
Yeah, good. So that's that step, which is different than this step.
That's right.
Right. Okay, cool. But they're related. I mean, they're related. Let's do this one. So here we go, f of 1. Now I want f of 1. And so I pay attention to where the equal sign is. Watch this. What if there wasn't an equal sign right there? Watch it. If there wasn't an equal sign there. Now I try to plug a 1 in. Well, when it's less than 1, you use this. When it's greater than 1, you use this. What about when it is 1? I think I would call it undefined. It ain't defined. And we would have failed right there. We would have failed step 1. Now, hold on. This is me making up problems on top of problems. That's not good. Hold on a second. There wasn't equal to this sign there, and here I go. I want to know what f of 1 is. I plug a 1 in where it says it's allowed to equal, and I plug in a 1. When I plug in a 1, it's the cosine of pi over 6. That's the cosine of 30 degrees. Everybody knows that's...
I don't have that.
Dude, it's a square root of 3 over 2. Cosine of 60 degrees. 30 degrees. Cosine of 30 degrees. Pi over 6. Anyway, that's that y value. What about number 2? Number two. Oh, shit, I gotta do the limit. I gotta do the limit as x approaches 1. Oh my God, you know what that really means. I gotta probably check out the left, and I gotta check out the right. Look at me, I'm getting a little sloppy, see me? A little sloppy notation there. But you know what I mean, right? Mm-hmm. I'm checking out the left and the right. To check out the left side of 1, that probably means you're less than 1, and you plug a 1 in here. See, again, you may stop and say, dude, you're not allowed to plug a 1 in here because it ain't equal to. Do you want to tell me that? I am allowed to plug in a 1 because why? Because I'm doing a limit. I am. I'm getting really, really close to 1 is what I'm doing. I'm doing a limit, so I'm allowed to plug in a 1, and I get 5, I get 5. On the left side of 1, I use this, I plug in a 1, and I get 5. That's the limit from the left. From the right, I'm on the right side of 1, I plug a 1 in here, and I get what I just got a second ago, square root of 3 over 2, and therefore, since the left and the right don't match, this limit does not exist. This limit does not exist, and we can stop right now and say this guy is a discontinuity. He failed the continuity test. He is a discontinuity, and he's non-removable, by the way,
Right.
at x equals 1. This is good stuff, man. This is good stuff. We're using limits to discuss continuity, and it's kind of fun and it's a little technical. My advice is understand these 3 steps. Go through these 3 steps. Unless you got a problem like this. What's this problem? I mean, there's really not that much investigating to do. I don't think I really need this is easier, okay? When I said, when you have a problem like this, these are easier, really. I mean, those piecewise things get a little crazy. I got to investigate the left, the right. This is so easy. I mean, really, all I'm looking for is where it might be undefined. I mean, I'm really kind of looking for this. Where is it undefined?
6.
Thank you. I mean, we should know that at x equals 6, the function's undefined. Do you know that, right? So that means it's a discontinuity. And it turns out, if you remember from your algebra classes, you know that it's an asymptote is what it is. This guy is a vertical asymptote. And if he's a vertical asymptote, he's non-removable. So he's a discontinuity and he's non-removable. I'm saying he's non-removable. He's non-removable because he's a vertical asymptote. That's what I'm saying. What did I do earlier? Hang on. What did I do earlier? I did this problem. This is a little different, but here's a problem. It's already all factored for you. I don't really need my crazy 3-step definition, or I mean, really all I need is step 1. I mean, when is this guy undefined?
1 and 2.
He's undefined at 1 and at 2. So at x equals 1 and at x equals 2, they're both discontinuities. And they're both undefined. But there is something different about them. Because this one can cancel away, he's a whole. And if he's a whole, he's removable. He's still a discontinuity, though. It doesn't make him not a discontinuity. That's the fun. He's still a discontinuity, but this one's a whole or removable. And this one is a vertical asymptote. So he's an asymptote, and he's non-removable. Are you guys okay? I mean, those were a little easier, right? You can just... All right, I'm going to tell you something else here. I want to go to 2.5, and this kind of ends the chapter here. I want to do this limit. I don't think so. Okay, now, so try to forget about continuity, maybe. I mean, I don't know. There's a lot of ways, there's different ways we can think. We can think visually. I mean, there's a lot of different ways to think through these math problems. And I try to show you different ways, to tell you the truth, but I think right now I'd like to think numerically. So let's forget visual for a second, and forget, this is a question, this is not really about continuity, it's about, can you do this limit please? And what's new in 2.5 is this idea of infinite limits, is what they call it. And let's see what happens. If I try to do this limit, I plug in a 4. Oh, remember, I told you, the first step of doing all limits is just plug it in and see what you get. If I do plug in a 4, what do I get?
0.
No, well, yeah, okay, 8 over 0. You didn't mean, I know you didn't mean 0. You meant, right, it means 0. You meant 8 over 0, right. I get 8 over 0, which is undefined, but with limits we don't write undefined. Maybe it does not exist. Maybe I should investigate it further. You know, earlier in this chapter, you know what was real common to get? It was real common to get 0 over 0. I don't know if you remember that, but you get 0 over 0, and most of those we could fix. We would factor them and fix them, or we would multiply by the conjugate, or we would get a common denominator. There's all kinds of algebra you can do to fix some of those 0 over 0s. Yeah, we were doing them analytically, kind of. We could 0 over 0, we usually could investigate and get an answer. But 8 over 0, that makes me think of undefined, but hold on, let's look at this. Let's look at this. The limit as x approaches 4 from the left. Let's look at from the left. Now check this out. So if it's from the left, all right, hold on. I'm approaching 4. I need a number line. I'm approaching 4 from the left. So what am I? I'm like at 3.9?
Yeah.
I mean, so pretend I'm a 3.9 for a second, or a 3.9999. I mean, whatever you want to do, but if you subtract 4, so I know I said plug in a 4 and you get 0, right? What I'm trying to figure out is which side of 0 am I on? Am I on the positive side of 0 or the negative side of 0? And if you're approaching from the left, you're a 3.999, and when you subtract 4, you're on the negative side of 0. See, I don't even want to call it a 0. I want to call it a little negative point. Oh, whoa, 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 whoa. I mean, it's a 0. But I'm on the negative side of 0, and I'm dividing into a positive 8. How many times does that little teeny number divide into 8?
Infinite.
Infinite. And because he's negative and he's positive, the answer is negative infinity. You all right with that? What I'm starting to do is I'm starting to call 0 not really 0. In limits, I'm saying 0 is a teeny weeny 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 number. And so how many times does it divide into that 8? A bunch. And so the answer is infinity. But hold on, I don't know up there, I don't know which side of 0 it's on. I don't know which infinity it might be. So this was good. This is a good problem. And I guess I kind of did it numerically. If I think about throwing in a 3.999, subtracting 4, I get this teeny negative number. A teeny negative number divided into positive 8 is a huge negative number. You okay? What about if you try it from the right? And maybe it's obvious, but from the right, now you're plugging in, you're coming from the right, so now you're plugging in like a little 4.001, like a 4.001. Anyway, when you subtract 4, you get 0, or a teeny weeny number that's on the right side of 0. Is that okay with you? You do get 0, but sometimes I put a little positive sign on it because I'm a positive 0. I mean, you know what I mean, right? It's a teeny weeny number on the right side of 0. That also is infinity, but now it's positive infinity. By the way, if the limit from the right and the limit from the left don't match, what's his answer? If the limit from the left and the limit from the right ain't the same thing, what's his answer? Does not exist. That's true. Right, you guys? When the limit from the left and the limit from the right are two different answers, does not exist. But listen, I want to say this. It does not exist, but it ain't about that 0 in the denominator necessarily. It's about the left and the right not matching.
Right.
Alright,
Yeah, go ahead.
okay. So what's not matched here? Like, I mean,
Well, here's what, okay, let's visually look at this problem. And again,
did you get it?
from your algebra days, you should know something about this. I mean, this is just a function, and it's undefined at 4. It's a vertical asymptote at 4 is what it is.
Right.
And you know how vertical asymptotes work. What we just investigated helped me a lot, though. When you approach 4 from the left, it dives to negative infinity. And so as you approach 4 from the left, it dives to negative infinity. As you approach 4 from the right, it goes to positive infinity. I mean, my limits just told me that, but if I recall my old algebra days, that's how asymptotes tended to act, right? If you have a vertical asymptote, the graph would go toward it. And you can sort of see, again, I'm saying this limit doesn't exist. I'm saying it doesn't exist because the left and the right don't match up. The book, sometimes the book argues with me a little bit, or I argue with the book. Sometimes they say when the answer is infinity, the answer does not exist.
Come down.
And I kind of get their point, right? If you're going to infinity, the answer doesn't exist. But hold on, if the answer is infinity, I'd like to know that. So I don't want you to write does not exist. If the answer is infinity, I want you to tell me whether it's infinity or negative infinity. Now, why did I write does not exist up here? Oh, because they weren't the same, right? Because this one was, from the left, it was negative infinity. From the right, it was positive infinity. That's why, to me, that's why he doesn't exist. If they both came out to be positive infinity, what would I put up here? I'd put positive infinity.
Oh, you would.
But the book might argue with me
Yeah,
about that.
because it's not bounded.
So it still does not exist?
Well, the book would say that. Screw it,
Right.
screw them. Do what I say.
Okay.
I want to know where the limit, I pretty much say does not exist for when the left and right don't match up.
Right.
If the thing's going to infinity and you can conclude it's going to infinity, then I kind of want that as an answer. I don't want to use does not exist for that situation.
Okay.
These are fun though. In 2.5, there's nothing too tricky, I think. I mean, again, you could go explore them visually and you get these answers right away. I mean, just look at this picture and you could type it in your graphing calculator, look at this picture and get those answers pretty quickly. I was asking you to think about teeny weeny zeros is what I was asking you to do, right? Teeny weeny numbers that are close to 0, either positive or negative numbers close to 0 is what I was asking you to think like that, which I think is cool too. But I'll quit today. I appreciate your attention. You should try a little 2-4, a little 2-5 homework, and I'll try to answer some questions Friday morning.